Okay, everybody, we're here for discussion 6.3, the final topic in Unit 6. We're going to talk about limiting reactants, percent composition, and figuring out what the molecular formula for a compound is given its empirical formula. Okay, so a limiting reactant. The definition of a limiting reactant is a reactant that runs out first in a chemical reaction. And the limiting reactant will determine how much of product will be formed in a particular reaction. Now, I like to use as an example making cookies. You know, I've used this example several times. Now, if I have 1,000 chocolate chips, but only 1 cup of flour, the flour would be my limiting reactant. It doesn't matter how many chocolate chips I have, because once I run out of flour, I'm going to be done making cookies. So we're going to make however many cookies 1 cup of flour can make. All right? So you're going to recognize limiting reactant problems because they're always going to have 2 given quantities. Now these are just stoich problems, and all the other stoich problems that we've done so far have only had 1 given quantity. So oftentimes the problem will say which is the limiting reactant, but if it doesn't, you'll know it's a limiting reactant problem because of those 2 givens. All right, so let's think about limiting reactants making turkey sandwiches. So we have 10 pieces of bread, but only 4 portions of turkey. How many sandwiches can you make? So to solve these problems, we're going to do the stoichiometry for each given quantity and find out how much each given quantity will produce. Whichever produces a smaller amount is the limiting reactant. All right, so we're going to use 2 conversion factors here. We're talking about bread and portions of turkey. And I know that one conversion factor tells me that 1 sandwich is made from 2 pieces of bread. So 1 sandwich equals 2 bread. I also know that 1 sandwich requires 1 portion of turkey, so 1 sandwich equals 1 turk. So now I'm going to do the stoichiometry for each given quantity. So I'm going to start with 10 pieces of bread. My conversion factor says that there's 2 pieces of bread for every 1 sandwich, so this way we're going to make 5 sandwiches. And that's not hard to imagine that 10 pieces of bread makes 5 sandwiches. Now, the next given says that we have 4 portions of turkey. And we know that there's 1 portion of turkey for every 1 sandwich, so 4 turkeys is going to make 4 sandwiches. So now we look at the amounts of each that was formed. Whichever amount is smaller is the limiting reactant. So turkey is our limiting reactant, and our theoretical yield of sandwiches is 4 sandwiches. So let's now do an actual example. It says sodium hydroxide reacts with carbon dioxide. 1.85 moles of sodium hydroxide and 1.00 moles of carbon dioxide are allowed to react. How many moles of sodium carbonate will be formed? So again, you can recognize this is a limiting reactant problem because there's 2 quantities that's given to us, 1.85 moles of sodium hydroxide and 1.00 moles of carbon dioxide. So let's go ahead and do the stoich for each individual given to determine how much product will form. So let's first start with sodium hydroxide, 1.85 moles of NaOH. If I look at the stoichiometric coefficients, I see that there's 2 moles of NaOH for every 1 mole of sodium carbonate. So 1.85 moles of sodium hydroxide will produce 0.925 moles. Now we'll do the same exact thing for our other given. Only here we have 1.00 moles of CO2. And my conversion factor I'm going to use is the mole ratio that says there's 1 mole of CO2 for every 1 mole of sodium carbonate. So 1 mole of CO2 will produce 1.00 moles of product. So I look at the 2 amounts, see which one is smaller. 0.925 is smaller, so my limiting reactant is sodium hydroxide. All right, so this example I would like you to try yourself. So pause the video and try to work it out, and then come back and see what the answer looks like. All right, so it asks us how many moles of hydrogen bromide are formed when we start with 13 moles of C6H6 and react them with 15 moles of bromine. So we have two given quantities, which tells us that this is limiting reactant. So we're going to do mole to mole conversion. We'll start with C6H6. So I have 13.0 moles of C6H6. If I look at the mole ratio, I see that there's 1 mole of C6H6 benzene for every 1 mole of HBr. So that much C6H6 benzene will produce 13 moles of product. And we'll run the stoichiometry for the next given quantity, which is 15.0 moles of bromine. So I see that there is 1 mole of bromine for every 1 mole of HBr formed. That means that 15 moles of bromine will form 15.0 moles of product. We look at both of the quantities produced. 13 is smaller than 15, so the limiting reactant in this case is C6H6. All right, percent yield. So percent yield is the experimental value divided by the theoretical value times 100. In other words, it's the amount that we measure in the lab divided by the amount that we expect to get from the math times 100. So an example of using this, if the actual yield of HBr in the reaction from the last example was 9.2 moles, what's the percent yield? Well, the theoretical yield was the one that we calculated with the stoichiometry. So that is going to be 13.0 moles. Now, the experimental yield is what we actually got in the lab, which is 9.2 moles. So to calculate the percent yield, we'll take the experimental, which is 9.2, divide by the theoretical, which is 13, multiply by 100, which gives us sorry, my calculator is dying, 70.8%. All right, another formula to use, fairly simple. All right, finally, using molar mass and empirical formula to determine a molecular formula. Just a little bit of review. Empirical formula is the smallest whole number ratio of atoms in a compound, and a molecular formula is the actual number of atoms in a compound. So just for a little practice, write the empirical formula for the following 3 compounds. H2O2 is hydrogen peroxide. We see that there are 2 hydrogens for every 2 oxygens. That means there's a 1-to-1 ratio between them, so the empirical formula is HO. C2H8, there's 2 carbons for every 8 hydrogens, so the empirical formula is CH4. And S6O22, there's 1 sulfur for every 4 oxygens, so the empirical formula is SO4. We should remember that. Okay, so a number of different molecular formulas can come from the same empirical formula. So here we have 3 examples, CH4, C2H8, and C3H12. All 3 of these compounds have the same molecular formula. Now, the only one that's an empirical formula, is CH4 because it cannot be reduced any further. But if we took CH4 and multiplied that formula by 2, we would get C2H8. Now we see that the mass of CH4, 1 carbon and 4 hydrogens, is 16 grams per mole. So if you double the formula, you will also double the mass. If we look at C3H12, that formula is 3 times the original molecular formula, and so is its mass. So if we know the empirical formula and the mass of our compound, we can calculate its molecular formula. Now, the steps to follow are as follows. 1, calculate the molar mass of the empirical formula. Then, divide the given mass by the mass that we calculated. Now, we're always going to see the mass of the molecular formula be some whole number multiple of the mass of the empirical formula, because every time you change the empirical formula, you will do the same thing to the mass. So finally, when you do that division, you get that quotient, you can find out how much bigger your molecular formula is than your empirical formula. So let's actually look at. All right, so here's an example. It says find the molecular formula of an anti-cancer drug called altretamine. Its empirical formula is C3H6N2 and its molar mass is 210 grams per mole. So the first step is to find the mass of the empirical formula. So we're going to take the mass of carbon and multiply it by 3 because there's 3 carbons in that empirical formula. We're going to add it to the mass of hydrogen times 6 and add it to the mass of nitrogen times 2. And when you do that, you get about 70 grams. Now the second step is to divide the given mass by the mass of the empirical formula. When we do that, we will find out how many times bigger the molecular formula is than the empirical formula. So the given mass is 210. When we divide it by 70, we get 3. That means that our molecular formula is 3 times bigger than our empirical. So we take our empirical, C3H6N2, and we multiply all the subscripts by 3. So when we multiply it by 3, we get C9H18N6. And that's how we do that. So this one I'd like you to do all on your own. So pause the video, do the problem, and come back and see how you did. All right, so it says the analysis of rocket fuel showed that its empirical formula is NH2. The molar mass of the compound is 32.05 grams per mole. What is the molecular formula of the fuel? So the first step is to find the mass of the empirical formula. So for nitrogen is approximately 14, plus the 2 for the 2 hydrogens gives us an approximate molar mass of 16. The given mass is 32. When we divide it by 16, we get the answer 2. That means that our molecular formula is 2 times larger than our empirical formula. So when we take NH2 and multiply it by 2, we get N2H4. And that is how we do that. Now that is the end of Unit 6. Please make sure you practice. That is the only way to get good at this. If you practice, I promise you will do well. Thanks again for watching, and have a great day.